If you remember from earlier, we said cloud is created from air that is being lifted, cooling adiabatically to dew point. Let us now consider the various mechanisms for lifting air to higher levels. We have discussed parcels of air being warmer, and hence less dense than their surrounds, rising up until perhaps they meet a temperature inversion. But what will be the trigger for these parcels of air to rise in the first place? The first mechanism is one we have already touched on, that of the Earth's surface heating a parcel of air. Consider this temperature-height graph. As the sun heats the Earth, it warms the air in contact with it by conduction, and so the air temperature rises. But remember, this does not happen uniformly. Areas with low albedo will warm up quicker than the surroundings. Therefore, the air in contact with these areas will be warmer than the surroundings. At 0700, we find a temperature of around +7 degrees Celsius. Notice that the air is warmer than the environment and will rise, cooling at the DALR. But as it rises, it eventually cools to the same temperature as the environment, the ELR. It will no longer continue to rise. However, whilst cooling, it never reached the dew point, and therefore no cloud has developed. At 0800, the temperature has risen to +8 degrees. But again, nothing much happens. The parcel of air will have enough buoyancy to rise up the DALR as far as the ELR, but it still hasn't reached the dew point. Therefore, no cloud will form. However, at 0900, with a temperature of +10 degrees, we can now follow the DALR up to a point where we meet the dew point, coming up from the surface value. Therefore, we are saying that we have lifted and cooled this parcel of air enough to reach saturation and hence form cloud. Notice that convection is a vertical movement of air, which in turn will produce vertically developed clouds. We know, of course, these are cumuliform type. At this point here, the surface temperature rose high enough to cause continued convection, which allowed the air to cool to dew point to create clouds. This critical temperature is called the trigger temperature for convective cloud. Below this temperature, the parcel of air reached the ELR before the dew point. Let us consider another scenario and think about the whole depth of cloud. With a temperature of +11 at 0900, we see air rising that is warmer than the environment, creating a convective cloud of this height and depth. At midday, with a surface temperature of +14 degrees Celsius, we can lift a parcel of air to this height, with this cloud base and top. Finally, at 1500 hours, with a temperature of +17, we get our maximum convection, with maximum temperature and the cloud tops going off the top of the graph. This is a reflection of what happens on many convective type days. At 0900, small cumulus clouds develop after a little surface heating. By mid-afternoon, with maximum daytime air temperature, the biggest convective cells develop, with possibly the greatest risk of shower activity. There are other ways of lifting air within the atmosphere. Convergence is another that we shall look at now. Convergence in the atmosphere means air is accumulating in a particular area, with an associated depletion elsewhere. Here we see a peninsula on a summer's day, with sea breezes blowing in across all coasts. There is an accumulation of air along the spine of the peninsula, and we say there is convergence along this line. Convergence can happen at any level of the atmosphere, but here we are concerned with low-level convergence. So what will happen as a result of this convergence? The convergence at low levels forces the air to rise, and we know what happens when air is forced to rise. It cools adiabatically, and eventually cloud will form as the water vapour condenses out. In some cases, the uplift due to convergence is strong enough to produce precipitation in the form of showers or even give thunderstorms. Look at this satellite image of the southwest of England. It shows a line of convective cloud which has formed partly as a result of sea breeze convergence. We have looked at a relatively small-scale example, but we can see convergence on a larger synoptic scale. For example, there tends to be an accumulation of air at the centre of an area of low pressure, and also along weather fronts. The convergence of air involved with these types of systems produces more widespread ascent of air, therefore more cloud development and precipitation on a larger scale. Even on fronts, as a result of convergent uplift enhancing convection, we can get cumulonimbus activity. Let us now consider uplift of air along a frontal zone a little more deeply. When air masses of different properties interact, the warmer, less dense air will be forced to rise, and frontal uplift can occur along the boundary. If we take a look at this image again, you can see that there is a massive cloud formed over a large area. This is an occluding frontal system, with much of the cloud you see lying along the cold and occluded fronts. But what causes this amount of cloud to form? We take a good look at the structure of fronts later on, but for now, look at a cross-section through a warm and a cold front. Notice how air is encouraged to rise up the frontal surfaces, due largely to the fact that warm air is less dense than cold air, and has a tendency to ride over the top of colder air. The presence of high ground will also, on many occasions, force the uplift of air and hence the formation of cloud. There are three main scenarios we shall look at. Firstly, in stable conditions, we get a lot of layered cloud forming over the high ground. Notice the lower cloud base on the upwind side of the high ground compared to the downwind side, where the moisture content is less. There may also be enhanced precipitation on the windward slopes. Another phenomenon can occur, which we saw in the lesson on turbulence. In stable conditions, but with a slightly drier atmosphere, we can often see a classic formation of cloud, called lenticularis. Here are examples of how they look. This type of cloud has a recognizable lens formation and is indicative of mountain wave activity, and hence a signpost of a moderate or severe turbulence hazard in the area. In unstable conditions, high ground will act as an enhancement to the development of larger convective cells. Here we see a cumulonimbus cloud forming over hills. This is reasonably common, with areas of high ground seeing higher precipitation totals and a higher risk of thunderstorm activity in certain situations. Sometimes these convective cells can be embedded in layered cloud, also produced by the forced uplift over high ground, causing a huge hazard for aviation. When air crosses over high ground, it often becomes slightly drier and warmer. Over the high ground, rain or snow is often produced, falling to the ground. This effectively removes moisture from the air and lowers the dew point. Another reason for the drying and warming is the entrainment of drier air from higher up in the atmosphere as our low-level air squeezes over the high ground. This gives a lower average humidity on the leeward side of the hills as the air descends. In Europe, this process is called the Föhn effect and results in higher cloud bases and a significant drying out of the air to the lee side of mountains. There is one important point to note about orographic cloud. The icing and turbulence risk over hills is greatly enhanced. The reason is relatively simple. The atmosphere is given greater vertical support, and as a result, more water droplets can be within the cloud. Generally speaking, the risk of icing is particularly great for the following cloud types: nimbostratus, cumulonimbus, and cumulus clouds. We are now going to look at cloud types, their classification, description and forms. Clouds can be categorized in several ways. One way is to split them into two types, cumuliform and stratiform clouds. This system is based upon how the clouds actually look to the observer. The cumuliform clouds are cumulus, cumulonimbus, altocumulus, altocumulus castellanus, which is a particular form of altocumulus that has a distinct importance, and cirrocumulus. The stratiform clouds are stratus, stratocumulus, nimbostratus, altostratus, cirrostratus, and cirrus. Clouds are also defined by the height of their base. So we have low-level clouds, stratus, stratocumulus, nimbostratus, cumulus, and cumulonimbus. Medium-level clouds are always denoted by the prefix alto. These are altostratus, altocumulus, and altocumulus castellanus. High-level clouds are given the prefix cirro and include cirrostratus, cirrocumulus, and cirrus. Let's learn some more about these cloud types. Here is a summary of the clouds classified according to their height above ground level. Examine this chart for a moment before continuing on to the next section.